Now we have the in the part 5, we have compared the two data set, which is MINST and CIFAR 10. So as in assignment 4, as was given by the professor, I got the accuracy in MINST and was around using the same thing was around 97. And in this week, after doing some things, we reached the accuracy of 76 using the same models. So let me explain you what happened. And in this part, we'll do the same. So the MINST data set contains 28 into 28 grayscale images, which is very important to understand. It's in handwritten digits. So CNN achieved the higher accuracy of 97.76 in this data set. The model converted quickly, reached for over 98% accuracy within 500 steps. So this is because MINST is relatively simpler data set with uniform backgrounds and centralized digits. Whereas the Safer 10 is, on the other hand, contains 32 into 32 colored images of various objects. The CNN struggled more with this data set, achieving the lower accuracy of 76%, which is not that good. This is due to the increased complexity of Cipher 10, which includes color images, diverse background, and high vulnerability within the class of the same thing. So as you can see here, I have compared that how the accuracy moved from 90 to 98, and the in CIFAR 10 how it moved from 40 to slightly increasing with every step to 95. So, and this the average rating. This is the average rating of both the things. So the MINST have the average rating of 97 and CIFAR 10 have the average rating of 77, which makes sense, right? So because it started with 40 with 400 steps and it started with 1900 steps. So this 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 performance that is showed is because of the performance gaps that we have. As you can see here, using the graphical representation of accuracy curve. So the CIFAR 10 started with from here from 0.4 to and went to 90 with a few things. And here the MINST was almost constant after, I guess, after 10 steps. Yeah, means 1,000 steps. After 1,000 steps, it was like really constant. So the observation from this is like the CNN achieves the significantly higher accuracy on the MINST dataset compared to the CSER 10. The MINST accuracy is start from 0.8. These are the same things which I've explained. So let's talk about the performance gap, yeah, which is very important. So there are four things. One is dataset complexity. As I've already told you, the CIFAR 10 is more complex dataset. The image size and channels. The CIFAR 10 images are larger and have three colors, while the MINST only have the two colors. You can say the grayscale images, and the images are smaller as well. Also, variability of the CIFAR 10 is higher because within the class, which is harder for the model to generate. And also the overfitting, which is very important. The CNN is less likely to overfit due to the simplicity of the data set. So, and in the CSAT, the more prone to overfitting due to the complexity of the variability of the data set. So it's very important. So these are the few suggestions that we have to improve the CFFI 10 CFR 10 CNN model. So the data argumentation, use the technique to rotation, flipping, and cropping the images for the diversity of the training data set, and deeper architecture. For example, the ResNat and VGG to compare with the complex features and regularization, apply techniques using dropout, weight deny to reduce the overfitting, and we can also use transfer learning, use pre-trained models like trained on ImageNet or other features. And this is the same conclusion. I'm not explaining conclusion because it's the same thing that because I'm explaining everything in detail. So let's now focus on how we can improve it. As I told you in previous slide here, that how we can improve it. I have used the same techniques. So in this part, we'll focus on improving the CNN performance on the Safer 10 dataset. So I have used the data argumentation. I have added the random horizontal flip and brightness adjustment and contrast adjustment to the training image. This increase the diversity of the training data and help the model to generate better performance and reduce the overfitting which is there. So the reason why we used it is to diversify the training and help the model to generate better and reducing overfitting. And then we have used the branch normalization. I have added the branch normalization after each convolutional and fully connected layer. This stabilized the training process and accumulated the coverage. And the third is learning rate scheduling. I have implemented the exponential delay for learning rate, which allow the model to fine tune its learning rate during training, which is very important for the model as well. So after applying all these things, we can see a substantial change. Uh, the training and adding the training placeholder to control branch normalization behavior during the training and testing data. During training, branch normalization use branch statistics, which is training true, and during testing, branch normalization using population statistics is training as false. So this really helped our data set in results. After implementing these changes, the model finally test accuracy improved by 90.07%, a significant improvement over original 82. This demonstrates the effectiveness of data argumentation, branch normalization, and learning rate scheduling in improving CNN performances. So, and the conclusion would be same as we have already explained here. The final test accuracy was 90.07. So let's move forward to the project report, which is the seventh part of our think for us. By now we have completed our project, and which with all the paths starting from the creating the data set, loading it on the like, loading it on the GCP, after that using TensorFlow for CNN, and then comparing with Minst, and then improving our CNN model. So let's now talk about the part 7, which is the project report. I have summarized the key findings and conclusion from the project. So I might be repeating all the things that I've already said. So the complexity of the dataset significantly impact the performance of CNN. Minst with simpler grayscale images allows the CNN to achieve high accuracy, while Cipher 10 with the color images does diversify the background and perform more challenging. The data argumentation technique like random flip, brightness adjustment, improved model generation, ability to reduce overfitting. The branch normalization stabilized the training performance and um, accurate the convenience and learning rate scheduling. The learning rate scheduling allows the model to fine tune its learning rate during training and leading to better convenience. in future, I would to experiment with deep learning architectures as well. So let's discuss about the conclusions of each steps. So the conclusion one is dataset complexity affect the model performance. The complexity of the dataset significantly impact the CNN, as we can see from all of our uh, coding. I have also attached the coding links, which um, yeah, in contrast, the cipher 10 dataset, which contains colored images with diversify background and higher vulnerability, prove more challenging and resulting in lower accuracy. This highlights the importance of the dataset complexity and determine the difficulty in classification task. The data augmentation improves generation. The data augmentation technique helped the random horizontal flip brightness adjustments, as I've already told you, and helped us to increase the accuracy from 82 to 90%. Normalization stabilize the training. Branch normalization is an effective technique to stabilize the training process of CNN by normalizing the input, and each layer of branch normalization help accurate conversion and improve the model performance. As in part 4, the addition of branch normalization after each convolutional fully connected layer convince the implementation of the accuracy of the model. So in the key findings, the complexity of the dataset significantly impacts the performance of the CNN model, as we have already discussed all these things. Um, and for the future work, I would say the experiment with deeper architecture like ResNet and VGG to future improve the accuracy. We can apply additional data augmentation techniques such as rotation and scaling to increase the diversity of the training data, explore the transfer learning or using the pre-trained models to leverage the training features from larger dataset. This project demonstrates the effective CNN for image classification task and highlights the importance of data complexity, data augmentation, and advanced training techniques in building the robust and accurate models. So, and I will upload this to the YouTube and paste the link here. And these all are my references. Uh, the TensorFlow document helped me a lot to find which are the um, TensorFlow uh, uh, the modules that I have to use. And this is the link to the C410 dataset and the convolutional network layer from the GitHub. This really helped me a lot to understand the CNN models. So in conclusion, this project has provided the valuable insight into the challenges of working with different datasets and the importance of employing the advanced techniques to improve CNN performances. I have successfully designed and implemented and evaluated the CNN model for image classification, and I hope this presentation give you a full and clear understanding of the work that I have done. Uh, s- uh, so this presentation include the link of the YouTube video. The YouTube video is provide the virtual walkthrough of the project and demonstrate the implementation of the results of the details and the findings. So thank you for your attention. I am happy to answer all the questions that you might have on this project. You can mail me. Thank you so much. Have a nice one.